logical equivalences involving quantifiers. That means two statements that involves or involving predicates and quantifiers are said to be logically equivalent if and only if. What is that condition? Statements, those statements involving predicates and quantifiers. That means P of x, Q of x, R of x, existential quantifier or universal quantifier or some universal quantification or existential quantification. So they are said to be logically equivalent if and only, what is their condition? If they have the same concept, same truth value. They have the same truth value no matter which predicates are used, which predicates are substituted, and which domain or domain of discourse. Only domain, or in some cases it is written domain of discourse is used. That means in the mathematical statement or logical expression, whatever the given domain or whatever the predicate, that is no matter. So we have to only show if these two statements or two logical expression have the same truth value, then we can conclude that they are logically equivalent.
So what you have written, sir?
Domain of discourse, domain of discourse, or in simply write domain, or it is the other name is universe of discourse. That is the other names of domain. That means in a logical expression, whatever the predicates and whatever the domain, but if we are going to show that they both the logical expressions have the same truth value, then we'll conclude that they are logically equivalent. Okay. The same notation we'll use. That means notation. That means that is same equivalent statement. Two statements. Let S, another is T, involving predicates and quantifier are logically equivalent. That is the notation is you can write S is equivalent to T, or you can use the symbol S is equivalent to T. That is the symbol of equivalence. So that for all x, P of x and Q of x, that is equivalent to for all x P of x and for all x Q of x. Also it is given that . the same domain will be used. So same domain is used throughout. That means both the predicates P of x and Q of x have the same domain. Okay. That means here what how many predicates are there? Two predicates. One is P of x, another one is Q of x. That means suppose we have particular predicates or two predicates. One is P of x and another one is Q of x. With a common domain or common domain of discourse, that is D. That means just that is we have taken two predicates P of x and Q of x. That two predicates we have taken. These two predicates have the same domain D. That means D is the domain for P of x. Also D is the domain of Q of x. So now we will prove this equivalent. That means if they have the same truth value, then they are logically equivalent. That means we will show two statements. LHS implies RHS. Conversely, RHS implies RHS. Then we'll say that they are equivalent. Okay. We'll prove this. First, we'll first the necessary parts. Suppose that first part, that is for all x, P of x and Q of x, we have taken that this is true, and let any element A belongs to the domain D. Then if that means for all x is applied to what? P of x and Q of x is true, then what will be true? If A is any element in the domain, then what will be true? That means see, for all x this is true. That means x may be A. So you can write P of A and Q of A is true. As for all x it is true. That means for all the elements in the domain this will be true. That means P of A and Q of A is true. Then P of A and Q of A is true. Then just expand the conjunction. What will be true? P of A and Q of A is true. Use the rule of conjunction. What will be this? This implies,
Both P and Q are true.
yeah, P of A is true and Q of A is true. That is the rule of conjunction. Okay. Now P of A is true and Q of A is true. What is A? A is any arbitrary element in the domain D. That means here the element A is arbitrarily taken from the domain of discourse or domain D. H A is any arbitrary element in the domain. So P of A is true. That means P of A is true for all the elements A. That means what? That means you can write P of X is true for all X. That means P of A is true. What is A? A is any arbitrary element in the domain D. So it is true for all X. Similarly, Q of A is true. That is the same thing Q of x is true for all x implies. So P of x is true for all x. That means what? In symbolical. P of x is true for all x. That means for all x, P of x is true. And Q of x is true for all x. That means for all x, Q of x is true. Now, this is true, that means for all x, Px is true. And for all x, Qx is true. Use the rule of conjunction. That means for all x, P of x conjunction for all x, Q of x is true. So we have taken for all x, P of x and Q of x is true. But we got that for all x, Px and for all x, Qx is true. That means this implies this. That means we got that for all x, P of x and Q of x. This implies for all x, P of x and for all x, Q of x. That is the one part or first part. We'll prove the converse part also. Conversely, we'll take the other part. We consider for all x, P of x and for all x, Q of x is true. And we'll take a element A belongs to the domain D. First simplify. For all x, Px and for all x, Qx is true. That means what? Use the rule of conjunction first. Use the rule of conjunction. That means for all x, P of x is true. And for all x, Q of x is true. Since A is what? A is any element in the domain D. So for all x, P of x is true. That means P of A is true. And for all x, Q of x is true. That means Q of A is true. So now P of A is true and Q of A is true. Take this rule of conjunction. This implies P of A and Q of A is true. What is A? Since A is an arbitrary element or taken arbitrarily. From the domain D implies P of A and Q of A is true. What is A? A is any arbitrary element from the domain. That means P of x and Q of x is true for all x. Okay. So P of x and Q of x is true for all x. So use the symbol for all x. That means for all x, this scope will be true. P of x and Q of x is true. So we have taken that what? We have taken for all x, Px and for all x, Qx is true. But we got that for all x, Px and Qx is true. This implies that, that means This implies that what, or we conclude that for all x p of x and for all x q of x, this is true, implies for all x p of x and q of x. That means we have proved that LHS implies RHS, also RHS implies LHS. That means for truth value. So as both the truth value are same, so we can conclude that both are equivalent to each other. Therefore, we conclude that that for all x, p of x and q of x, that is same as or equivalent to for all x, p of x and for all x, q of x. Okay. Now, negation of quantifiers. So, there are two quantifiers. One is negation of for all x, p of x, that is equivalent to what, n. Another rule is negation of existential quantification, that is there exists x, p of x. What will be this? Their negation of for all x px, that will be equivalent to there exists x negation of p of x, and negation of there exists, that will be for all x negation of p of x. These two laws are called De Morgan's laws for quantifier. See, that means first one is universal quantification, second one is existential quantification. So, negation of universal quantification, so negation of for all, that will be there exists x, then negation of p of x. So, negation of there exists x p of x, that is equivalent to first negation is applied to there exists, that will be for all x, then negation of p of x. Okay. We'll prove the only just one proof, then we can do the other. Consider first we'll take negation of for all x p of x is true. This is equivalent to what? Any idea? Negation of for all x px is true.
Sir, there
Then
exists x negation of px.
no, we are going to prove that one also. You cannot use this. Their negation of for all x px,
Yes, sir.
that is equivalent to their existence space. We are going to prove this. Okay. So if negation of some expression is true, then we know that for all x px, that will be also true. If negation p and negation p, their truth value of p and negation p are opposite to each other. If p is false, negation p will be true. Like the same is negation of this is true, then this will be false. Got it or not? Okay. Then tell me when universal quantification is false. That means what? universal quantification, that is for all x px is false. That means what? Yeah, tell. Universal quantification is false. That means there is an element x in the domain for which the given predicate px is false. That means universal quantification will be true when it is p of x is true for all x. So universal quantification will be false. That means there must have an element in the domain. For that element, the given predicate will be false. That is also equivalent to there is an element x in the domain for which, see, p of x is false. That is equivalent to what? P of x is false. That is equivalent to which statement? Negation of p of x is true. That means instead of writing p of x is false, we have written negation of p of x is true. Then tell me, there is an element x in the domain. For that element, this statement is negation of px is true. That means what? That means there exists an element x. For that element, negation of px is true. That means there exists x, negation of p of x is true. So we have taken negation of for all x px is true is equivalent to there exists x, negation of px is true. That means they are equivalent to each other. For second part, you can prove negation of there exists x, p of x, that will be equivalent to for all x, negation of p of x. That is your work. Okay. If the domain contains finite number of elements or n elements, such as x1, x2, xn, then you can also prove like this for finite number of elements, negation of for all x p of x is equivalent to what? Negation of for all x px. So negation is there for all x px. Then what is equivalent statement for all x px when the domain contains finite number of elements? That is to negation is there. So that universal quantification for all x px is same as or equivalent to what? We have studied before that. If the domain contains finite number of elements x1, x2, x3 up to xn, then the universal quantification is same as or equivalent to what? Equivalent to the conjunction p of x1 conjunction p of x2 up to p of xn. So negation of for all x px, that is equivalent to negation of this. This can be written as p of x1 conjunction p of x2 conjunction like this, conjunction p of xn. Okay, this is equivalent to, so negation of this, negation of p of x1 and p of x2 conjunction is there, that will be same as using De Morgan's law, negation of P of x1 disjunction negation of P of x2 disjunction negation of P of xn. Then this will be equivalent to what? That means, see, we know that if the domain contains finite number of elements, then P of x1 disjunction P of x2 disjunction up to P of xn, that is same as existential quantification. So there exists x P of x, but instead of P of x, it is written negation P of x1 conjunction disjunction with negation P of x2 up to negation P of xn. So that will be negation of P of x. You can also prove like this: if the domain contains finite number of elements, then also negation of for all x px, that is same as or equivalent to there exists x negation of px. Also like the same way, negation of there exists x p of x, that is equivalent to for all x negation of p of x. Okay. Find the negation of the given statement. Statement is given, there is an honest politician using predicates and quantifiers. That means find the negation of the given statement. Given statement is there is an honest politician. So using predicates and quantifier. So how to use? See, first we will introduce a variable. So using that variable, we will choose a predicate. Using that predicate, we will convert the given English sentence using logical expression using predicates and quantifiers. Okay. Let P of x, that is the predicate, will introduce a variable x to politician. So there is an honest politician. So P of x, we have written, let P of x, that is the predicate, x is honest. That means, see, we have to, what is predicate? Predicate is the statement, the proposition that always involves a variable. So without variable, that is not a predicate. So P of x, we have to we are choosing a predicate P of x that denotes x is honest. So using this predicate, we will convert the given sentence, there is an honest politician, to logical expression. After converting logical expression, then we will go through the negation. So the given statement, that is there is an honest politician, that is given, is represented by, what will be this? There is, which quantifier we will use? There is an honest politician, where the predicate is x is honest. Existential quantification, that means there exists x, p of x, where we have to choose the domain, where the domain, what is the domain here? Domain consists of You have to choose from the sentence. There is an honest politician. So we have chosen X is honest. So what is X? X is the politician, any politician. So a domain consists of all politicians. That means, see, now see, there is an honest politician. That is the same sentence as there exists X P of X. X is any politician. So there exists a politician who is honest. That is the same thing. There is an honest politician. We have converted this English sentence to logical expression using predicates and quantifier. So quantifier is existential. So there exists X, P of X. Okay. Now, our aim is to find the negation of this sentence. As we have converted the English sentence to logical expression, there exists X, P of X. So, if we are going to find the negation, that is the negation of this logical expression. That means the negation of the given English sentence, that is same as negation of there exists X, P of X is what? Negation of this. That means negation of there exists X, P of X. That will be equivalent to what? Negation of there exists X, P of X. That is what? Use the De Morgan's law. What is that? Negation of there exists X, P of X. See this, that is,
Sir, for all x, negation px.
yeah, for all X, negation of P of X. So that is the negation of the English sentence. So that is the logical expression. We have to convert this right side expression in terms of English sentence by using De Morgan's law. So now, what will be negation of P of X? So we are recording negation of P of X. So as P of X is honest. So what will be negation of P of X?
Sir, x is dishonest.
Yeah. So our requirement is for all X, negation of P of X. What will be this? For all X, negation of P of X. That is the negation of the given statement. So first we have converted the given English sentence or English statement to predicate and quantifier. That is there exists P of X. The negation of this, that is the same thing for all X, negation of P of X. So as we have chosen P of X, that is X is honest. So negation of P of X, that is X is dishonest. So what will be the English sentence or English statement for all X, negation of P of X? For all means for all X. X is what? X is any politicians. For all X, that means all politicians or every politician. You can write every politician is. That means for all X, negation of P of X. Negation P of X is dishonest. That means for all politicians, those who are dishonest. That means every politician is dishonest. That is the answer. Any doubts? First, the given sentence choose a variable and use a predicate. Using that predicate, convert the English sentence to a logical expression using predicates and quantifier. After converting to logical expression, then find the negation of that using De Morgan's law. Then after finding that logical expression, again convert to English sentence. Okay. find the negation of the given statement that is given all Americans eat cheeseburgers using predicates and quantifier. Then choose a predicate. Let a predicate is q of x. Then what will the predicate? Choose a variable x. All Americans eat cheeseburgers. Then choose a predicate. All Americans eat cheeseburgers. So the predicate contains the variable x. Then what will the predicate? X eats cheeseburger. That is the predicate. So now using this predicate, we will convert the English sentence, that is English statement that is given, to a quantification. That means, so the given statement that is given, all Americans eat cheeseburgers is represented by what? Where domain is? What is the domain here? All Americans eat cheeseburgers. What is the domain here? Domain consists of all Americans. Domain consists of all Americans. So what will be all Americans eat cheeseburger? Convert it in terms of logical expression. All Americans. All means for all x. Q of x. Where the domain consists of all Americans. That means for all x, q of x. That means every Americans, for all Americans, same. For all x, x eats cheeseburgers. That is the same meaning. All Americans eat cheeseburgers. Okay. Now we are going to find the negation of this. The negation of for all x, q of x is given by negation of for all x, q of x. What is that? That is equivalent to what?
There exists x negation qx.
Yeah. There exists x negation q of x by using De Morgan's law. So now we are going to express there exists x negation of qx in terms of English sentence. So what will be negation of q of x? Q of x is x eats cheeseburgers. What will be negation of q of x?
X doesn't eat cheeseburgers.
Yeah. Then our aim is what will be negation there exists x negation of q of x. That will be equivalent to what? Or that will be English sentence. There exists x negation of q of x. There exists x means you can write there is. X means what? X belongs to set of all Americans. So there is an American. So that negation of Q of X. X does not eat cheeseburger. X means what? X means American. X means you can write who. So there is an American who does not eat cheeseburger. That is the answer. Also, you can use then tell me any other English sentence expressing same. There is an American who does not eat cheeseburger. There is means at least one. There exists at least one American. So there may be more Americans, more than one. That means you can use the word instead of there is. You can use some other words instead of there exist. So you can use some. Some Americans does not eat cheeseburgers. That is not required. That is the answer. That can be also answer. That means see, all Americans eat cheeseburger. The negation of this sentence is some Americans does not eat cheeseburger. Or you can add there exists at least one American who does not eat cheeseburger. That is the negation. Using predicates and quantifier. Okay. Express the sentence or given statement. That is, sentence is given. Every student in this class has studied calculus. Express this English sentence using predicates and quantifiers. That means we are not going to find the negation. Only express this to logical expression that involves predicates and quantifier. Then first we will introduce a variable x. So we will introduce a variable x so that the given statement or given English sentence becomes what? That is, every student in this class has studied calculus. So we'll introduce a variable x. Every student, that student may be x. So you can write for every student x. For every student x in this class. Then every student in this class has studied calculus. For every student x in this class, that student has studied calculus. You can write x has studied calculus. Here the domain of discourse of domain. What is the domain here? See, in this case, you can take two types of domain in this class. Every student in this class, you can take all the students in this class. That will be the domain. If you are taking the domain of discourse is the set of all students, in this class. I have taken that as a domain. That means domain is set of all students in this class. That means for every students we are taking. That means always that in the class we have taken it, that is domain. So we have to consider a predicate. Let predicate is C of X. Let predicate C of X is X has studied calculus. Then the given statement can be expressed as, what will be this? Every student in this class has studied calculus. We have taken every means for all the students. That means that will be for all x, C of x. That is the answer. That means we have chosen the domain. Domain is all the students in this class. That is important here. If we are taking all the students in the class, that means for all x. For all x means what? For all the students, those who are present in the class or those who are student in this class, C of x. That means C of x means x has studied calculus. That means those students, for all the students in this class has studied calculus. That is the same thing. Every student in this class has studied calculus. Okay. But if you are choosing another domain, the answer may be different. We'll see that. Okay, just it will take. See, in the same question, we can use in an alternative way. That means if we change the domain, first we have taken the domain is set of all the students in this class. Instead of taking that, if you taken the domain to consist of all people, we are not taking that all the students instead of those in this class. That means we are taking instead of those in this class. Instead of taking those students present in this class, we are taking to all the peoples. Then what are the changes? Then we'll need to express the given statement as, that will be, so every student, as we have taken the domain is all the people, so we change the statement. That same sentence will be for every person x. For every person x, if that person x is a student in this class, then that person has studied calculus. Instead of student, we used person. That means for every person x, If that person is a student in this class, then that person has studied calculus. That means here we have to consider two predicates. One is s of x, that is the person x, that is a student in the class. Person x in the class, or is a student in the class. Then c of x, that we have taken the same, x has studied calculus. Then the given statement, every student in this class has studied calculus. That will be same as can be expressed as what, that for all x, if for all x means x is all the peoples, for all x, if that person is present or is a person is student in this class, that means if s of x, then c of x. You can write the person x, the person x is a student in the class. That means the same statement can be used in two different ways. That depends on the domain. If you are taking the domain consists of all the students in the class, so that is for all x only c of x. If the domain is all the peoples, that means for all x, x may be all the people. So in that case, you have to choose the conditional statement. If that people or person present in is a student in this class, that is s of x, then x has studied calculus. Okay, we'll stop here.
So can we also add this question as for all x means
Yes.
as
For all x,
so can we also write this question as means for all x s of x and then and
no, and you cannot use.
y, sir?
See, and means what? S of x means x is student in this class and has studied calculus. No, that is not the case. If see every for all is you, that is if in that case of there exists, you can use the and. In case of for all, you have to use the conditional statement.
Then sir we can also give the condition existence x of cx.
Yeah.
Okay, sir.
Let me see. In the that depends upon the domain only. See, in the first case we have taken the domain. If you are taking the domain, all the student in this class, that is x. X means what? That is the student in the class. If you are taking for all x c of x, what is for all x? That is x depends on what? Domain. If you are taking domain consists of all the students in this class directly, so for all x cx, that means that every student in this class has studied calculus. Only simple sentence. If you are taking, instead of taking all the students in this class the domain, you are taking all the peoples as a whole. So from whole the people for all x, that means for all the people, if that person is student, then he or she has studied calculus. That is the case.
Okay, sir.
Yeah. So like this, you have to solve some problems from the exercise 1.4. Okay. Okay, I will give the attendance. Okay.
Thank you, sir.
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 So solve some problems from the exercise. We will also solve some exercise problems 1.4 if you want.